Now from ML and chemistry to ML and neuroimaging, we are
really hard to take over from a fantastic speaker like you. I'm already at a disadvantage. I belong to Center for Brain Research. It's an autonomous center housed in IISc. The newest building in IISc. It started with a generous funding from the Government couple. This is our mission statement. So the objective is to have some kind of scientific discovery, some kind of intervention to come up with, so that neurodegeneration can be delayed or maybe reversed. And there are about 3 main projects that we do there. These are huge flagship projects. The first is called the Sunspot. We've identified a small village close to Kolar called Srinivasapura. There is a huge farming community and they are all assessed every now and then. So it's a huge longitudinal study. So there are multiple assessments they are made, lots of cognitive tests that they go through. So we've recruited about 10,000 people there who are 45 plus. And this study will go on for 15 to 20 years. It's one of the world's largest longitudinal study on rural population. What is it that we hope to achieve? We want to have some findings which are specific to Indian population and not just pick up things from the Western population. These are some of the snapshots of the kind of works we do. We have a huge team, medical doctors included. So they come over for scanning, they come over for multiple assessments. They are asked to apply certain interventions in their life to see if things are changing. There's yet another project which is funded by the Tatas. It's called the TMSA. It's again a longitudinal study to study neurodegeneration. Here we have about 1,000 recruits. So the goal is to see nature versus nurture. That is, does urban lifestyle versus rural lifestyle? Are there any risk factors? Are there any protective factors? What kind of intervention will delay neurodegeneration? The third is called Genome India. It's a huge project across various institutes. We see lots of IITs here, IIScs here that participate in this. The hub is Center for Brain Research. What is it that we do? We are trying to see if we can have precision medicine. The kind of diversity we have in our country, is it possible to catalog the genomic sequences? So these are the main 3 things that happen at Center for Brain Research. Now let's get on to the talk. This is how I have sequenced my talk. You just see some certain basics about brain and some popular neuroimaging tools that all of us must have seen. And one very special neuroimaging tool that Professor Jagannathan spoke of a little earlier, called MRI, magnetic resonance imaging. And in all of these, we'll see how machine learning plays a role. Now, just some basics of what our brain is. So we know it's a connectionist architecture. What does that mean? With the same constituents, different people are good at different things. Why is it? Because of the kind of connections we make. You play piano for long and those connections become stronger. You paint for longer, you make those connections strong. You practice maths, you get better at it because you're making those connections strong. So depending on what connections you are strengthening, you are getting better at it. So that's the connectionist architecture. So we have 4 main parts. All of us have learned it in high school, right? Cerebellum, brainstem, limbic system. But I want you to look at the cerebrum closely. Why is it? Most of our cognitive functions happen there. So all the sensory inputs, when you see, when you hear, when you touch, all those those inputs are being processed in the cerebrum. So that's a very, very special part. What is it about the cerebrum? We have some lobes, 4 lobes for studying. The frontal lobe, parietal, occipital, temporal. Now, no matter what activity we do, there are certain networks which are in action. And the regions belonging to those networks are spread across these lobes. To study any activity, you will have to study regions which are spread across these lobes. What is the fundamental basis of brain? Is the neuron. The cell you are seeing here. No, that's it. Okay. So we have a neuron. It's made of 2 distinct things. You see cell body right at the center. Sorry. You see cell body. There are various inputs that are entering the cell body. Those are called the dendrites. And then there's a long output that is coming out of the cell body, and that's the axon. So what do we see? These axons, they have a coating of myelin sheath. And why is it? That is so that the electrical impulses that we generate can be transmitted faster. So that's an evolutionary success. So that is why we are able to, that's why we are called intelligent. We are able to think faster. So the whole of brain consists of 2 different types of matter, grey matter and white matter. Grey matter is made of the cell body, and the connections between them are made of white matter. Why white? Because the myelin sheath is white. And because these connections are all important, to study degeneration, you will have to look at degeneration of the white matter. A very, very popular neuroimaging tool. So we have lots of electrical activity happening in the brain, which means if you study the electrical activity, it will tell you something about the functioning. What is the best way of studying the electrical activity? You have electrodes placed on the skull and you're measuring the electrical activity. So as many electrodes, so many waveforms, right? So very primitive ones will have even 1 electrode. A little better, at some primary health centers, you can get about 8 electrodes. You want to do better, you can have 64 electrodes, 128 electrodes. The more electrodes you have, the more densely you can study the activity of the brain. So the graphs you see there are the electrical activity that are picked up from the electrodes. So what is the order of electrical activity here? It's a few microvolts. It means your electrodes have to be very, very sensitive, and you should know how to work with this kind of signals. How old is this? About 100 years old. So for about 100 years, people have been doing this. And way before that, it was done on animals also. So it's as old as the mountains. So the very first neuroimaging tool you learn about is EEG, the electroencephalogram. So what can be done with this? It's very popularly used to diagnose seizure. So when there is no seizure, that is when the person is free of seizure, the electrical activity seen is very different from when there is seizure. What happens when there is seizure? You see lots of spikes, lots of activity, lots of wiring which is happening. So this is one very easy tool to diagnose seizures. What else? Sleep staging. So when we sleep, it happens in several stages. You're at first kind of awake, and then you get into rapid eye movement, you get into non-rapid eye movement. There are stages there, and then you're very close to waking up. Each of these stages are very well studied. The signatures of each of these stages can easily be seen in EEG. So what is the point I'm trying to make? That EEG signals carry signatures of every activity that the brain does. Right? Now these are very stark. Is it going through seizure? Are you sleeping well? What about the finer things? Such as, you must have have seen this, right? So there are cars on the track. Can you use your EEG to control it? You just look for racing cars using EEG. You'll find lots of links on YouTube. I didn't want to play the video here, but this is a very much done thing. There's nothing surprising in this. You've heard of this company, Neuralink? Yes? Who owns it? Elon Musk. Because we know Elon Musk, we know Neuralink, right? Yes. So what happens there? So they are trying to come up with advances that can be like lifestyle changing. So what you see here on the right is a person who cannot move any of his 4 limbs. They are called quadriplegics. Yeah, maybe that's the pronunciation. So using an implant in his brain, it is possible for his limbs to move and he can feed himself. That's a very big achievement, right? But then this is invasive. That's the price. Now, there's a lot of things that can be done using EEG. What does BSCAI stand for? Do we know? Any of the students? It's general knowledge now. Brain-computer interface, right? You pick up some signals from brain, you program it and try to do something. So what typically happens there? There's a frequency band decomposition of the signals. So certain frequencies are meant for certain activities. It's very well studied. And then within each frequency band, you compute some statistics. What kind of statistics would you compute? Mean, variance, kurtosis, right? And then you extract some very well-known features. Entropy, energy. So these are very well-known. They've been used for decades. What do you do with these features? You feed them to a classifier. You obtain a classification label. What do you do with that label? That label will decide the action. So this is a typical flow of work in a brain-computer interface. But there is something which is phasing it out, and that is deep learning, where you do not need to know a priori what is important. You let the system learn from the data what is important. So we did a simple experiment where we tried to assess something fine, like the level of creativity in an activity. So this experiment was carried out on normal subjects. So the question we tried to ask is, just by using EEG signals, can I tell, is the subject doing a creative task or a monotonous task? So the task one, the subject is given some random lines and curves and he is asked to make a drawing out of it. Just the way we do storytelling, right? You're given some phrases, you connect them and make your own story. The second task was very monotonous. You just draw vertical lines. So I pick up EEG signals while the subject is performing the 2 tasks. Using EEG signals, can I say what task was he performing? So this is the kind of picture we gave, some random curves, and this is what we expected the subject to complete. You use those curves, use the dots, and make a drawing. So this was the experiment timeline. It's done over 5 minutes. At first they are shown the unfilled canvas. So the subject gets 1 minute to plan, and then there is a brief period of rest. And then there is a timeline where he makes the drawing. Then again there is rest, and then he does the monotonous task. Can anyone tell me why this rest is needed? Why didn't we ask the subject to do it continuously? Why is rest needed between tasks? Yeah? Not so hard at all. Yeah?
Create the capacity.
Capacity? Yeah. you help differentiate, yes. There's a lot of inertia, right? So when you're doing something, you tend to continue doing that for some time. So you allow that to settle down and then you make your measurements. So this is one sample drawing that we got and one sample of the monotonous task. So we are collecting EEG while all this is happening. And what did we see? So we used the deep learning based framework. So we converted the time series to images in one approach. We converted the time series to a video in another approach. And we used the computer vision based classification that we had. And this is the kind of accuracies we got. So don't worry about the numbers. The bottom line is creative tasks can indeed be identified using EEG. This is without any prior knowledge, without knowing what kind of frequency band would contain signatures of creativity, without knowing anything, just using data and deep learning. We'll move on to the next neuroimaging tool. So wherever there is electricity, there is another field associated with it. What is it? Magnetics, yeah? So just as we have electroencephalogram, there is something called magnetoencephalogram. So what is it that they are trying to record? They are trying to record the magnetic fields that emerge out of electrical activity in the brain. So needless to say, again, it is very, very small. The order is 10 power minus 15 Tesla. You remember Professor Jagannathan gave us the table about conversion from Tesla, Gauss to Tesla, right? So it's very, very tiny. It means you really need to have a huge array of receivers which are very, very sensitive. They are called squids here. But what all can be done with it? You study activity, brain functioning, cognitive processes. A lot of things can be studied with it. But it's not portable like EEG. Right? EEG can be taken to any good primary healthcare center. But to have MEG, you have to create the facility. You have to create a place where the magnetic fields are isolated from the rest. So what all can be done with MEG? So this is from one of the papers that I was seeing. The subject speaks something and you do not know what he has spoken, but all you have access to are the magnetic fields that you are recording. You just put them together, you can train a neural network to figure out what is it that he was talking. So in this case, the person was saying goodbye. So those were two very simple neuroimaging tools which were essentially looking at activity aspects. Now, can we have a neuroimaging tool that can cover a host of aspects? Now, when you want to study the brain, can you think of what all aspects you would like to cover? One is activity. What else would you like to cover? Thinking capacity. Yes? Anything else? What would you like to study about the brain?
Monitoring dementia.
Dementia, yes. What changes happen when there is dementia, right? Yeah? Emotions, autism, whether brain transplant can actually be possible. That's ambitious, right? Whether the person is lying or not lying detector, yes, that's very much there. Short-term, long-term memory. How do we form memories, right? How do we learn? Neuroplasticity. Understanding consciousness. These are very, very ambitious, yes. So there are a host of things we'd like to study, right? Let's look at the gross things that have been possible in the last few decades. The very first image brain, you are looking at a modality that can give you good contrast. When we take pictures on our mobile, we don't like it when our face is not visible, if we merge with the background, right? Because you want to see the details on your face. So you want to have a modality that can translate differences in tissue. By differences, what do we mean? How can you differentiate tissues? Our chemistry teacher would tell us chemical differences. Are they the only one? Mechanical differences, magnetic differences. So you just name it and you should be able to differentiate tissues. And what magnetic resonance imaging is famous for is soft tissue contrast, as Dr. Jagannathan was saying. So here's a brain, and I'm telling you that there's a tumor there. Are you able to see the tumor? If you squint, maybe try harder, there's something that might emerge. Do you see it somewhere? I'll show you another image. Do you see the difference? That is what contrast means. What you want to image should be highlighted, should be very different from the background. Why is this useful? Why do you want good contrast? The surgeon wants to plan this surgery to remove tumor. You don't want any healthy tissue to go out, right? So every curve, every serration should be very, very clear. So this is one good thing about it. So what are we seeing here? There's some experiment that's being conducted. So the pink and blue lines you see, those tell you when the person is doing the task, when is he resting, right? So that is a time series that we are recording. How are we recording that? We are recording the entire volume of brain over several time stamps, right? So the cubes you see there, each cube has the subject's brain, and this is repeated over capital T time stamps. So capital T could be 100, 200, 500, depending on the length of the experiment. And how do you want the spacing between 1, 2, 3 to be? Do you want to be 10 minutes apart? Do you want it to be 1 hour apart? You want it to be as fast as possible, right? You want to acquire volume after volume as quickly as possible. So what do you think is possible now? What are the kind of speeds we can achieve? Do we do it every nanosecond? Do we do it every second? Do we do it? How good is it? Nanosecond? That is ambitious. So this is critical for understanding temporal dynamics. It requires at least sub-second sampling, right? Nanosecond is way too second. So what curve are we seeing here? The HRF curve, that's called the hemodynamic response function. So every activity that we do, if we consider the brain to be a linear system, it's as if the activity rectangular pulse that we see is convolved with this impulse response. Yeah. I want to say some things about magnetic resonance imaging, why it is so good. Are you controlling? Yeah? So the main thing, yeah? I do. Yeah. So the main thing about magnetic resonance imaging is, as Dr. Jagannathan was saying, what is it that we image? We image the water protons. So we have a natural element that can be imaged. So what is it about water? It consists of hydrogen protons. These can be seen as magnetic dipoles. And under the influence of a very high magnetic field, these dipoles behave in a very nice way. They all align along the magnetic field, but some of them align against the magnetic field. So we have two different energy states. The difference between these magnetic poles, that is used for imaging. How do we do that? We excite by giving some energy. So here it is RF energy. So the ones which are in the lower energy state pick up the energy and go to the higher energy state. And then what do? You cut off the excitation and let them relax. So how do they relax? By giving off the extra energy that they picked up. So when they are relaxing, you acquire energy and you get your image. or this is how it's done. What the scanner sees is what you see on the left. That's case space. To obtain your image, you have to do a Fourier transform and arrive at your image. So with magnetic resonance imaging, it's possible to study structural details when you look at the gross anatomy. It's possible to study neuronal tracts. You can look at tufts of neuronal tracts. And with functional imaging, you study brain activity. So if you're listening to me right now, you know which part of your brain is active. If you're speaking, you know which part of your brain is active. So this is one last thing that I want to end it with. There's a company that's come up, several companies that have come up based on what is called mind's eye. There's a person watching images, and you only have access to his functional MR images. Using that, can you tell what is it that he's watching? As you can see here, the one that is highlighted in red, that is chosen as the image that he's actually watching, which is very much true. Even in complicated scenarios, you see there are several groups that have come up with this, with different variations of how to reconstruct the image that the person is watching. These are fairly simple scenarios. Even when the background is so cluttered, you see it's possible to reconstruct what is it that the person is watching. So in summary, there is no better way to study neuroimaging than to apply machine learning. Thank you so much.
So I'm sure you have some questions. Any questions on that?
Closer to lunchtime.
Yeah, any questions from the rest of the audience? If not, we will thank Dr. Sinha for a really wonderful lecture. I request Mr. Shukri sir to be honest. Yeah.